So maybe we can gradually start. Welcome to the last seminar AESOP colloquium of the semester. This is a final week, and I'm glad to see a good number of our students are here. It's my pleasure to introduce our speaker today, Professor Rajiv Rao. Rajiv is an associate professor in electrical engineering as well as the Institute for Systems Research. His research interests include compilers, embedded systems, and computer architecture, compiler approaches to reliable software in embedded systems, memory allocation for embedded systems, and compiling to VLIW processors. Rajiv got his PhD from MIT in 2000. He's a recipient of a number of awards, including the National Career Award and George Corcoran Award for Teaching in Excellence in 2003. He was also the finalist for the Inventor of the Year Award in 2005 here on campus. Rajiv served as a workshop chair for a number of meetings, including ACM Conference on Compilers, Architectures, and Synthesis for Embedded Systems. And he has had many activities in the department and institutes, and today he's going to talk about his exciting research. So with no further ado,
Thank you, Reza, for that introduction. Thank you all for coming. This is a talk that's going to be about some of the research I'm doing here at the University of Maryland in collaboration with our collaborators, primarily Dr. Alan Sussman in computer science, as well as Dr. David August at Princeton University, and some people at BAE Systems as well. So, what I'm going to tell you about today is an automatically parallelizing compiler called AESOP. And, well, it's meant for high-performance computing. It's meant for parallelizing software. I'll tell you what all these things mean in a minute. So, to set the background for why we need parallelism, consider that according to Moore's law, the amount of silicon area on chip doubles every 18 months. And that is still true. However, what has happened since about 2004 is that clock speeds are no longer improving. This is widely known. As a result, most vendors have responded by putting multiple cores on chip, because you still have this area. That is the only way to use that area in a productive way. So one downside of having all these multiple cores is now you need software that can adapt to multiple cores automatically. So you would like to get parallel software in order to speed up your execution. Now, the problem here is that most of the world's software is serial. So we have this very strange situation today, where perhaps 95+% of the world's software is serial, but 99% of the commodity desktop and laptop hardware and servers are all parallel. So we've got this mismatch between the capabilities of the two. Now, is that a problem? Well, it depends on what you're doing. For example, if you're building a web server, it's not really much of a problem. Why? Because you've got all these web requests that are coming in from all over the world. They are independent. They don't depend on each other in terms of their results. So you can run them on different cores, and you get good utilization of multiple cores. Same thing with database servers and other servers. The problem occurs is when you've got one task that's compute intensive that you want running faster on a multiple core than on a single core. The way that most software is, as I said, unless you do something special, it will run on one core. So this is true, for example, if you've got a Core i7 today, which has got 4 cores. My laptop here has 4 cores, and each core can support 2 threads, so it's really 8-way parallel. But virtually everything I'm running on my laptop is serial. So it's using 1 out of those 8 threads. And the remaining 7 threads, well, they run any other task that I might have running. If those tasks are not compute intensive, then, well, too bad. My compute intensive task is still no faster on that 1 thread. It's as if I didn't even have the remaining 7. So what do I do about this? What do we do about this situation? Well, we would obviously like to get parallel software. Now, our approach is the following. It's to build a compiler that does automatic parallelization. Again, let's describe these terms. What is a compiler? So a compiler, as many of you probably know, is a piece of software that takes as input an application program that you may have written, and it produces as output a transformed program. For example, this transformed program might be an executable that runs on your hardware. On the other hand, it could be transformed not just to merely run as a machine code program instead of source code, it could also do extra work, such as it may also do parallelization, such that the input is serial code and the output is parallel executable code. Now, this is obviously nice to do because much of the world software is available as serial. If you want to rewrite it as parallel explicitly, it will take you time and money to do so. Again, that leads to the question, but why not just simply write parallel software? And that is a legitimate choice. And if you've got software that really doesn't exist in serial form anywhere, and you're writing it for the first time ever, maybe you should write it in parallel, if you care about its performance. But, and often there's no choice. You have to write parallel software by hand because there's no good parallelizing compilers existing today. This is, what I'm describing is cutting edge and ongoing research work. So there are, especially commercially, if you want to go buy a good parallelizing compiler, there is no such thing, unfortunately. But why not again write parallel software? There's a price to pay in writing parallel software. It's a perfectly reasonable alternative. Some people do it. You get good performance, but we should be cognizant of its cost. And one is lower productivity. It takes longer to write parallel software than to write serial software. Now, different parallel languages may have different costs. Some languages ask you to do more, some ask you to do less. Recognize that. But even with the simplest languages, there is, at least with the traditional architectures, there's a significant extra work you need to do when you're writing in parallel. Why? Because when you're writing in serial, you're concerned only about the algorithm, your method that you're trying to encode. When you're writing in parallel, in addition to your method, you've got to be concerned about things like parallelism, sequence that talks to another, what happens when there's sharing of locks, critical sections, and a whole bunch of extra things you need to worry about when you're writing parallel code, which you don't have to worry about in serial code. So there's a higher cost associated. And this is one of the reasons why even a lot of new code that's been written in industry today is being written as serial code because it's just too expensive to write parallel code. Expensive in terms of programmer time. And that's the most expensive resource there is. Right? You've got to pay people, have larger teams, take longer to write parallel code. Of course, it's also more error prone. You're thinking about all these parallel codes, you can get race conditions, a whole bunch of other things. And another thing is that, let's say you spend a great deal of time writing code that's optimized for one architecture. The problem is it's not necessarily optimized for another architecture. So if a new architecture comes by with a different number of cores, a different cache hierarchy, different network topology, if you want to get the best performance, you may have to re-optimize the code. So there's a significant amount of work doing. So when you write manual parallel code. And then the last one, this is perhaps the least well known, is that programmers actually may not find good transformation sequences to get good performance. Now, there's this belief out there that programmers in general, a skilled programmer, will always produce better code than even the best compiler. That is true. If you're talking about a really skilled programmer who's steeped in parallel computation, knows about all the issues. However, if you're not an expert programmer in parallel processing, the quality of the code you will produce will probably be quite suboptimal. And the reason is that finding these transformation sequences. Now, what are transformation sequences? It's when you change the program from the form you wrote it in originally to some equivalent form, which does exactly the same thing, but gives you better performance. So changing the form of the program is very important. Let's say you have two programs that do exactly the same thing. Doesn't mean that they will get you the same performance. And compilers are very good at searching through, or can, in theory, be very good at searching through these transformation sequences. And this is very, very key. I will later focus a lot of my talk on this particular problem of why it's so hard for programmers to look at these sequences and what are the issues involved. Okay, so again, why is it hard to produce good parallel code? Why can't programmers just write good code? And again, none of these apply for the really skilled programmer. But these are things that stand in the way. Number one, that just if you only concern yourself with maximizing parallelism, that actually counterintuitively does not necessarily give you the best results. Because there's more to modern processors than parallelism. Yes, they're parallel, but you also need to optimize for two other things, which are equally sometimes important. One is granularity of parallelism, meaning what you would like is you want tasks that run for a while. So if you've got two tasks, A and B, and you want to run them at the same time, if A and B run for a long time each, then you're likely to get good performance. On the other hand, if A and B are very short tasks, you're likely to get very poor performance if you run them in parallel. Why? Because often at the end, they need to exchange some data, or they need to signal to somebody else saying that we're both done. That's called synchronization. This whole thing of one thread of computation informing another thread, something about its status, is called synchronization. This cost of synchronization can be pretty severe because you're communicating messages across cores. And that's why it's really a bad idea to have things that are very fine-grained that run in parallel, at least on traditional architecture. And then the last criteria is caches. As some of you may know, modern processors don't just have a bunch of main memory. They also have another piece of memory called cache memory that's much closer to your processor pipeline. It's redundant in that it stores nothing other than what's already in the main memory. In fact, it only stores a small portion of what's in the main memory. But the reason it's so important is because it's much closer to the processor and therefore can be accessed much more quickly. It so turns out that modern processors all use caching, but the way your caching behaves depends very much on the nature of your code. So some forms of code can exploit cache reuse, meaning you touch the same data again and again in cache, which is a good thing because then it's already there in your cache. That happens a lot more with certain forms of the code than other forms. And I'll explain this a little bit more later. So if you want good performance, you want to be able to transform your code such that you get good cache use. The problem is, if you're writing parallel code by hand, you got to keep all these three in mind. If that wasn't hard enough, you also got to keep in mind that these criteria may even conflict. So you may come up with a way of writing a program that may maximize parallelism, but it may actually worsen granularity and cache behavior. Or in the process of trying to fix cache behavior, you may worsen parallelism. So it's not very clear what the best form is such that you take the total cost of all of these things into account. So how does that happen? And the other reason why it's hard to produce parallel code by hand is that these transformation sequences can be complicated. I will describe some of these transformation sequences for scientific programs and multimedia programs that I'm involved. There are these things, so I'll talk about what these are a little bit later. So, given that, our hypothesis here is that it's better, well, it's a claim, our hypothesis. Our claim is that it's better to automatically parallelize serial software, especially because in many cases you already have it. You don't have to do any work to get it because somebody already wrote it. So the problem with existing approaches to doing automatic parallelization is that it's been somewhat disappointing. People have been trying to do this for the last 30 years. There's been some success, and we are building on top of that success. But the end result has been somewhat disappointing in that there are no really good commercial compilers that do this. There are, even the Intel compiler, which is otherwise a good compiler, it even has an automatic parallelization option. Unlike most other compilers, it actually has an option. Performs rather poorly in fact. So much of this research has been in research prototypes, and they tend to, many of them, focus on one criterion. So they may, for example, there have been a bunch of papers published on what do you do to get the most parallels. There's also papers published on what do you do to get good cache behavior. And there's other papers talking about granularity computation and work scheduling and all that. The problem is you've got all of the above to take care of. So where do you, how do you trade these things off? And that's a problem that's relatively poorly understood. So we, as a response to this, we meaning my collaborators that I mentioned in Princeton and University of Maryland, and I, we have been building this compiler called the AESOP compiler. And AESOP is a parallelizing compiler, meaning it takes serial programs as input and produces parallel programs as output. Now, what are the two salient things about it? Well, one is it does a whole bunch of system characterization, meaning it learns about the architecture underneath, and it uses the results of that to inform the compiler optimization. So it will figure out, for example, how many threads, how many parallel contexts can you support. It's not just merely the number of cores, it's the number of parallel contexts that you can support. It'll figure out, do you have L1 caches, do you have L2 caches? What are the sizes of these L1s, sizes of L2, associativity, line sizes, sharing behavior, barrier costs, what's the different barrier costs to use, what are the best synchronization mechanisms to use. So it'll figure out a whole bunch of things about your computing platform automatically. So this is mostly work by Professor Alan Sussman in computer science, right, at the university. And he has written, along with his students, a bunch of these things called micro benchmarks, which are tiny little programs which aren't really meant to solve any real problem. What they are meant to do is probe the underlying hardware. And using these micro benchmarks intelligently, you can answer all these questions that I talked about, meaning the characteristics of the hardware. The second thrust is, once you've got all this information, use it to do automatic parallelism. So number one, you consider the parallelism, but you also consider granularity and cache performance. So we consider all three, and we also consider the underlying platform. So we look at the cache, the network, the number of threads, all of that, and in the end, hopefully produce a good couple.
What is the acronym?
AESOP, well, you know, this is part of the DARPA project. This was funded under, this is, I have to admit that we came up with this as a last minute, something like automatic execution for software, some, you know, everything, Department of Defense, everything has to be an alphabet soup. But you know, in the end, I like to think of as this Greek philosopher who's trying to think of the best way to practice. Yeah, it's something. All right, so now, as those of you who may have messed with compilers know, that it is notoriously hard to write a compiler from scratch. Despite my pretensions of being a compiler expert, I decided that this is not a good thing for me to be doing a compiler from scratch. Because there's a tremendous amount of work required even to build a serial compiler, leave alone a parallel. So we said, let's begin with a compiler that somebody else has developed. We looked at GCC. It's a widely used open source compiler. It's also the most horrendously written compiler that I can imagine. Internally, it is a mess. It is hard to use, hard to extend. So we decided to use LLVM, which is another open source compiler, less widely used than GCC, but it is pretty widely used. I mean, it's been around for about 10 years now. It came out of the University of Illinois. It's now maintained by Apple computers. In fact, they believe that their plan is to eventually move all of Apple's compilers to the LLVM platform. It's got thousands of users worldwide, and most importantly, unlike GCC, it's got a very clean and modern design internally. It's got nice class hierarchies, it's got good IR intermediate representation, all of that. So it's, you know, all this nice stuff. It's got an active developers community, you know, it's got people looking at commercially using this, it's extensible, and it's got good endorsement. Okay. So we take the LLVM compiler, add parallelizing routines to it, and that's AESOP. Okay. So the static characteristics, what do we collect? Well, much of the stuff I already told you. You know, we look at the number of parallel threads, then we look at processor characteristics like what the instruction timings are for different instructions. We count the number of registers available. We look at the sizes and the line sizes, the latencies and associativities of each level of cache. We look at the, whether the caches are shared or not, are they private? We look at a little bit about network topology, and also what costs it entails for synchronization. Okay, well, enough about background. Let's get into the nitty-gritty of how do you parallelize code. Now, it turns out parallelizing code is hard. If you want to parallelize code in general, it's harder still. So we said, let's focus on the one domain of applications that are usually the most required for performance, and also the ones that are easiest to parallelize. It turns out those two things are the same thing in this case, which is scientific and multimedia computations are the ones where you need the greatest amount of parallelism and good performance. It's also the ones that are most highly analyzable. Our team, however, has more to it. Like David August at Princeton is looking at non-scientific codes and non-multimedia codes. So he's looking at general purpose. There's a trade-off. You get less parallelism there, but it's more widely applied. So I'm going to focus on the scientific computation portion because that's the portion being done by my research. Okay. So what is affine parallelism? Affine is a short form for, it's just a fancy word which means linear. So let's say you've got a loop like this one. Now this is actually a doubly nested loop. So you've got for I equal to 1 to 100, for j equal to 1 to 50. Inside that you've got some computation of arrays A, B, and C. And these are two-dimensional arrays, so they've got indices something like I comma j. That means, row I, column j. Right? So now this piece of code happens to be affine. Now what's an affine piece of code? It's when you have code that consists of loops with induction variables. These variables called I and j are called induction variables. If this means a variable that's a counter variable, it means a counter variable, a variable that counts in a regular striding pattern. So you've got I and j, induction variables, and you've got array indices that are linear combinations of I and j. So if you've got ai plus bj plus c, that's a prototypical linear function. It means where a, b, and c are constants. Then you have ai plus bj plus c, that's a linear function of I and j. If it turns out all your array indices are linear, then this program is called affine. Now you may say, okay, that's a very specific class of applications. Why should I care? The reason we care is because somebody did a study years ago, this has been known for decades now, is that well over 95% of scientific codes are either fully or predominantly affine. All scientific and multimedia programs, so gaming, scientific codes, oil exploration, weather simulation, image processing, they're all affine. They're all affine. So this is good because these array indices, when they're linear, can be analyzed a whole lot. Our goal is to automatically discover parallelism in this kind of loop. Now in this particular loop, actually there's parallelism coming out of my years. I mean, every iteration is parallel. There's 5,000 iterations. And every one of them can be run in parallel with every other. Now why is that the case? Because no iteration depends on any other iteration. There's no such thing as loop carry dependency. So you have a thing called a loop carry dependence when an iteration depends on another iteration. In this case, we got none. There are no such dependencies. Now it so turns out we're not always so lucky. Let's look at this loop. This loop is sort of similar to the previous one. It's got I going from some lower bound to upper bound, j going from lower bound to upper bound. These don't have necessarily constants, but in here you've got the same kind of code. So this is also affine because I plus 1 is affine. So this is j affine, linear. But there's a problem. The problem is all the iterations are not independent. Why? Because let's say in iteration 5, if j equal to 5, you're writing a of 5 comma something. If j equal to, you're writing, if I equal to 5, let me take that back. If I equal to 5, you're writing a of 6 comma something. But in the next iteration, when I equal to 6, that's when you're reading. So you're reading what was written by the previous iteration of I. So you cannot execute different iterations of I in parallel because every iteration of I depends on the previous iteration. However, all is not lost because in this loop actually, the iterations of j are parallel. So you can execute them independent of each other because there's no such dependence on j. So how do you discover this automatically? I mean, we can as human beings look at this and that's not worth a whit unless the compiler can discover this automatically. So it turns out this is not something we did. This has been known for a while. There are these things called distance vectors that can categorize dependencies between these iterations. In this case, it's 1, 0. It's a vector. This simply means that along the I dimension, every iteration depends on one iteration before. On the j dimension, there's 0, which means there's no difference. So once you know this, you're in good shape. You can say, aha, I've got at least one dimension here that's got no dependence, so I can parallelize along j. What does this mean? How do I do that? Well, let's look at this. This is a simple picture of a two-dimensional grid here, and we call this the iteration space. What this means is the columns here are I, the rows here are j. I could have drawn it the other way, it doesn't really matter. But so I and j, and let's say these 4 lines are the set of, each point here is an iteration. So let's say you have a point here, I equal to 3, j equal to 2. That point is the iteration 3, 2. All right? So now, if I divide the iterations in this whole space into 4 chunks, such that this runs on thread 0, this is thread 1, thread 2, thread 3. Remember, I'm talking about threads here, not necessarily cores, even though most of the time they're one and the same thing. They need not be one and the same. So you've got 4 threads here. They are running a subset of the iterations. If you do it this way, you're in good shape. Why? Because you're parallelizing along the j dimension. Different iterations of j are running in parallel with j. If you tried parallelizing along the I dimension, you would break your code. You would get wrong answers because you're violating this loop carry difference. So you're not allowed to parallelize it like this. You must do so like that. Now, however, you can immediately see there are more problems here. Number 1, just because I get parallelism now, does that mean I will get good performance? Well, the fact that I'm getting parallelism along the outer loop I is actually good, because it means my granularity is high. I'm parallelizing fairly long pieces of work, meaning entire iterations, entire nested loops. If I had parallelism along the inner loop, I'd have granularity. But then cache, I mean, am I striding along cache lines? For those of you who know what a cache is, it's got these strips of code that are called cache lines that are brought in from the main memory at one time. When you access one element, you get the others for free. And you really want to get those, you want to use those others, otherwise you're going to lose. That's called cache reuse. And you want to make sure that you're getting cache reuse. Does this do that? Well, it depends on the way the cache is laid out. And it's a little involved to figure out what that is. I'm not going to drag it. But it may be, it may not. And we have to look at the exact access patterns. Okay, so we've already talked about the need for program transformation, so that you may not have parallelism along any dimension. That's one problem you may have. Or that the fact that the cache performance may be poor for a certain group, and the granularity may be low. Now, just because these problems are present in the original loop doesn't mean the compiler can't do anything about them. The compiler can change the loop, and that's called program transformation. There's a whole bunch of program transformations. They're like tools that a workman may use. If you're a workman, you've got presumably a whole set of tools, some of which may be applicable for a certain task, but the workman has to rely on their experience to know which ones to use and in what order. Something like that. So the compiler too has tools. It may interchange loops. That's called loop interchange. It may say, if I've got a loop saying for I for j, I can change this to make it for j for I. Why would it do that? Because that might fix the way you're striding along caches. So instead of striding across cache lines, you might start striding along cache lines. But that only may happen. If you do it helter-skelter, if you do interchange helter-skelter without knowing what you're doing, you may do the opposite. So you've got to be careful about that. Granularity. Now, this way, interchange can be very valuable. Let's say you parallelize the inner loop, which means the tasks that you're parallelizing are just iterations of the inner loop. They're very short running. You're unlikely to get good performance because your synchronization costs are going to kill you. There's going to be a barrier at the end, and that barrier is going to slow everybody down. Because at the end, they're going to all say, hey, we're all done. That mere act of saying we're all done can take hundreds of cycles. So this can help you with granularity. It can also help you with other transformations. So loop interchange is not merely good on its own. It's because it may make other transformations legal that otherwise weren't legal. So that's why this is a good argument. But fission is also nice. What's fission? Fission says, I've got a loop with a big body. I might want to break the loop in half. Now it may not be in the middle. I may reorder the instructions and then split it. So there's a lot of things about fusion. Now why may I want to split a loop into two? Because if I split loops, I may reduce the cache footprint of a loop, which means maybe in some cases make it more likely that my cache footprint will actually fit in my cache, thereby giving me good cache performance. So fission can really help some loops. Granularity, on the other hand, you pay a price. You're always going to lose something because you're going to have that barrier cost now twice rather than once because you split it. Parallelism, well, this may actually help you. Let's say there's two loop carried dependencies. One of them is loop carried along I, one of them is loop carried along J. The way I showed my earlier picture, you'd say, oh, no, I can't do parallelism along I, and I can't do parallelism along J either, which means I've got no parallelism. But I can do something about it. If I can split my loop intelligently, I might put one loop carrying dependence on one loop, the other one on the other, and voila, I have both loops being mapped. So nice things can happen when I split. Fusion is another thing I can use. Caches can sometimes really start improving their cache sharing if I fuse loops. I've got two loops, they both access the same elements. If I fuse them, I get much more temporal and spatial locality. Those are somewhat technical terms for cache reuse, but basically it means you get much better performance. And of course, I reduce my value cost to granularity. Loop reversal, what does this do? It just goes, instead of from 1 to 100, it goes from 100 to 1. Why is that a good idea? Not by itself, it doesn't do anything by itself. But it may make fusion legal, because in order to fuse two loops, the iterations have to look the same. So if you've got one of them going from 1 to 100, the other one going 100 to 1, you can't fuse them unless you reverse the second, and then fuse. So this is an enabling transformation. Now there's a whole bunch of, the problem with this whole space is that there are so many tools. There's loop peeling, and that can, I'm not going to go into each one of these in detail. Loop peeling says, put the last few iterations in a separate loop. Why might you want to do that? Because then fusion might become legal where it was not earlier. Unrolling might become legal when it was not. Skewing, what's that? That one is interesting because it can actually make loops parallel when they weren't. How do you do that? Well, let's say you've got a loop with a diagonal distance vector. So instead of the distance vector being 1, 0 or 0, 1, whatever it was, 1, 1. So you've got a 45-degree angle distance vector. Well, now you've got parallelism along neither dimension. That's bad. But you've got parallelism along the diagonal. So you can parallelize like that. And loop skewing exposes that in a very nice way. So it can, so that kind of thing can happen. Tiling is another thing. So this one, tiling is interesting. It actually, all it does is it improves cache locality by just taking what's within a thread and changing the order of what's within it. Strip mining, well, that's something, what it does is it takes one loop and splits it, makes it into two loops. Why may you want to do that? Because when you do that, the outer loop, which is called the outer strip mine loop, now might enable tiling because you can be interchanged with something. So, there's a whole bunch of complications here. And then, there's DSWP, which is decoupled software pipeline. It's a non-affine transformation being done by our collaborators at Princeton. And this has it do funky things that most people doing scientific computations wouldn't consider. For example, you've got a loop that's otherwise parallel, but it's got a print statement in it. Well, a print statement serializes your computation because you've got to print out the things in the right answer, in the right order, right? I mean, if the user printed out 10 statements in a certain order, you're not at liberty to go and change the order, right? So, therefore, what do? It ruins your parallelism. DSWP can change that by restructuring the loop by taking your print statements out and putting them somewhere. So there's all kinds of interesting things that can happen. Now you can see, my God, you're going to look at this and say, he just described like 9 transformations. And this is not even the end of it, there's more. And the problem is, it's not just one transformation that can be applied to a loop. There's actually sometimes you have loops in which you have a sequence of transformations. 5 transformations in a certain order have to be applied. And if you do that perfectly right, you get great results. If you do that in any other order, you do 4 out of 5, or you do the same 5 but you do them in the wrong order, you get no performance. Nothing. So it is a very, very carefully tuned algorithm. You have to get it exactly right, otherwise it doesn't work. So what do we do? Well, this is our model on how we solve this transformation order sequencing. And we have these 3 modules called critics. Now this is work that was built on top of, again, work by Princeton. Those guys came up with a thing called parallelism. We added 2 extra critics called granularity and cache. And then we come up with transformations as fixers. So we've got these critics saying, hey, I've got this problem. I'm not parallelizing enough, or I'm not my granularity is too small, or my cache is getting misses along this dimension or something. And these fixers will come and say, hey, each fixer gets queried. Can you solve this problem? So the fixers come one by one and solve problems one by one. And in the end, if you've got 10 problems, you've got 10 fixers, or maybe 7 fixers, because some of them can solve more than one problem. You can solve all. So the problem is, it's not as clear cut as what I'm saying. Because some fixers, in solving one problem, may introduce another problem, which is not necessarily a bad thing, because that other problem may be fixable by some other transformation. So there's a lot of different ordering that can happen here. So what we've got is an intelligent problem-driven search technique, which we use, and that searches, it searches through the transformations based upon the problems identified by the critic, rather than blindly searching through all possible transformation orders. Because if you start searching through all possible transformation orders, it's an exponentially large space. You may or may not ever find the right one. In fact, it's more than exponential, because it's exponential if everything can appear only once. If you've got n transformations and everything appears once, and everything must appear once, well, then you've got n permutation of n factorial orders. It's not n factorial in this case. I'm just giving you that as an example. It could be more, it could be less, because you may not need to use all of them. On the other hand, some transformations may appear more than once, in which case it's more than n. In any case, it's a very large space. It's an exponentially large space. I'm not going to get too much into the nitty-gritty of the search, but here's a picture that combines this parallelism critic idea and the negotiator idea from Princeton University with some of the stuff we've done. So here's the transformation decision algorithm. It's part of our compiler. What it does is it takes in the serial IR, the intermediate representation, meaning the serial program, and produces an output, the lowest cost transformation sequence. So the transformation sequence that results in the best performance. How does it do that? Well, each of the critics start identifying performance problems. They tell the negotiator what those problems are. The negotiator is another piece of software that queries the fixers. The fixers are all these different transformations I might have. The orange ones are affine, the green ones are non-affine. Orange ones are at University of Maryland, green ones are at Princeton. In a combined way, these negotiators will come up with these things called offers, which are possible solutions and possible solution sequences. Then we do something extra called determining the best loop order. That's some extra work we do here at UMB. Then we run something called the static runtime estimator, which estimates for each one of these possible candidate offers as to what their cost is. And at the end, we go with the lowest cost sequence. Now, you may repeat this whole process iteratively until we find better and better solutions. There's a lot of detail hidden in here. I can't possibly describe all the math to you, and I won't even try. But this is, it's meant for a fairly high-level picture here. So this is what it is. Now, just to show you that this problem of having multiple transformation sequences and how hard it is to get good performance is not just some theoretical claim on my part. I wanted to show you some preliminary results that we got on an 8-core machine. So this is an Intel Core i7. It actually has, I believe, no, actually this was on a machine that actually has 8 cores. Each core has one thing. It's not a Core i7. It was some other kind of Intel. I don't remember. Aparna, do you remember what dash was? Intel Xeon. It's an Intel Xeon computer with 8 cores. So these names like Gember, 3mm are programs, and I've got 6 of them. I'm showing you 2 of them here. I'm going to show you the others. We've actually got many more, but I'm just showing you a small sample. So let's see what happens for Gember. I'm showing you runtimes for 1, 2, 4, and 8 wake up. So what happens when you parallelize? 1 means the serial, and 8 means 8-way parallel. Then you've got the original loop. Here's the runtime with parallelization. Then this is with one transformation, another transformation, still more transformations. Let's see what happens. So the original loop for Gember did actually fairly well. You initially, what is this number 1? 1 is the normalized speed up for the original loop on one core. So we call that 1. There's underneath some number of seconds or cycles, but this is the normalized. We treat that as a speed up of 1. So 1.94 means that it ran 1.94 times faster on 2 cores than on 1. That's actually pretty good, because in general, you are not supposed to be able to run more than n times faster with n cores, because that's an upper bound. You've got n cores, you can't run more than n times faster. So it looks like on 4 cores you're getting 3.65, that's also pretty good. 8 cores you're getting 6.64. But what's going on here? It turns out if you take the original loop, then you do a loop interchange, then you do a fusion, then you do a strip mining, and then you do another interchange. In that exact order. Here's what you get. On 1 core, with no parallelism, the performance improves from 1 to 1.75. So it runs 75% faster with no parallelism. Why? Because you improve cache performance. That's the big deal. And this is, what does this compare to? This actually compares with GCC minus 03. So we benchmarked against GCC. The speed up of 1 was using the highest optimization level on GCC, which is widely considered to be one of the best serial compilers around. So we're actually discovering things that even state-of-the-art compilers don't. Then you might have said, hey, wait a second, didn't you say that you're never supposed to get more than a speed up of n on n cores? Well, we do. So here on 8 cores, our program runs nearly 10 times faster. How is that possible? Well, it's possible because in addition to parallelism, you're also getting cache performance. So that's why this is called super linear speed up. You're getting more than linear speed up. And that can happen. So you can see that, what's the bottom line here? Transformations happen. That's the bottom line. You can go from this first row to the last row and get a very significant boost in performance if you use our transformation sequence. Now this is not just for this program, 3mm, it actually turns out it's a relatively simple transformation sequence. You just apply a loop interchange and that does the trick. You go from like 1 to 1.6 almost. You get 1.6 speed up on just 1 core. And then you get like a speed up of 12 on 8 cores. And you could go to other, like ADI is another program, that the original loop had that, and again, if you apply strip mining plus interchange plus fusion, those 3 in that order, you get this. It goes to speed up of 3.3 to 3 speed up of over 7. Covariance, another benchmark, another program. Here's the original loop. This one's got to be the champion in terms of cache performance. You're getting a speed up of nearly 6 without any parallelism whatsoever because of cache performance alone. So this tells you just how important cache performance is. You can make a program run 6 times faster just merely by changing the order of striding the cache. So in this case, you end up getting fantastically super linear speed. Again, caveats here. This is for scientific programs, it's for small kernels, and these small kernels are often used as components of larger programs. But it shows you the potential here of the search strategies. This work is still under development, otherwise I would have shown you much larger. Yeah.
So these loops are originally parallel. Is that when you say original?
No. This is the original serial loop compiled using GCC minus. Yeah, I mean the whole goal of our project is that we are going to begin with serial code, and we're going to just you're right. If it was already parallel with a skilled expert programmer, you're unlikely to do better than our own results. But again,
so GCC is finding the code.
Well, no, actually, GCC minus 03, I mean, from what we discovered, I mean, I don't think the version of GCC we're using actually does any parallelization at all.
So those games are just...
But it does purport to do cache optimization, except it seemingly doesn't do it very well.
But you're running it on 2, 4, and 4.
That's using AESOP. So the only thing that's running on GCC is this, the one case. Every other number here is coming from AESOP.
If you write on the LLVM without the optimizations, would it be better or worse than that?
If you run it on LLVM, without any optimizations, LLVM alone actually gives you, it's in general not as good a compiler as GCC is. So it's unlikely to even in fact match the performance of this one. So if you use AESOP, don't use it for compiling serial programs. I mean, that's not what it's for. But it turns out, I think from Aparna, I think what we got is, I think the performance of LLVM and GCC, at least for these programs, was somewhat similar in the one process case, right? Yeah.
So very small, so LLVM is small.
Yeah. So for the kind of programs, these programs actually LLVM and GCC give you nearly the same speed. I mean, within a few percent of each other. So ATAX is another program. This is coming to the end almost. You see it goes from a 1.43 speed up on 8 cores down up to 6.6. So, you know, and your stream does again, you know, some improvement. And another take home here is that not all transformation sequences just keep, you may think, okay, you know, he's got like what, how many transformations here? Fission plus loop interchange, so strip mining plus interchange, 4 transformations. That means if you do 4, that's great. That means if you do 3, maybe it's less great. 2 is even worse. You think it's some monotonically increasing sequence length. No, it's not. So this is interesting. So if you see, if you apply just fusion, performance goes up. But then if you take fission, performance goes up. But then if you take fission and interchange, it worsens. The performance goes down. But then after you apply interchange, that enables you to do strip mining and another interchange. And that's when you start seeing performance that actually exceeds what you started with. So the lesson here is that sometimes in order to get to a long transformation sequence that's optimal, you may have to go through a path where the intermediate steps are nowhere near optimal. And you may have to take, so that stuff is going on. So that's another thing that complicates the research. It's not merely that you just keep adding transformation.
Just maybe this is off tangent, but what is the impact of this on power consumption?
Power consumption. Okay.
You achieve the high performance.
Right. So in general, there's 2 answers here. In general, multi-cores, if you want to look at the peak megaflops, that is, if you want to look at the best way of getting a certain number of megaflops, it's better to do it with many cores than 1 core. Why? Because if you want to build a really high performance single core, you have to burn a great deal of power to get it. So having more low power cores is a better strategy. So in that sense, it helps. It also helps for another reason. Power, well, energy is really what we're optimizing for, which is power into time. If you make programs run faster, you reduce speed, time. So therefore, your product of power and time goes down, even though your power is actually still the same. Therefore, your energy goes down. So if you make programs run faster, you usually consume less power. Energy. Which is what you really care about. So yeah, it does reduce energy consumption. Now the question is, what would happen if you ran it on 1 core? Would the other core still be active? Well, that's where things start getting great. Most of the time, modern processors are fairly good, although not perfect, at turning things off. So the impact on energy is mixed. In general, my expectation is this can only improve energy consumption. There's no way it can reduce it. But that, we haven't measured that, and that wasn't our time. But yeah. Okay. This is, I think, my last slide. As a transition stream, I wanted to mention that in addition to supporting serial programs, where we parallelize them to parallel code, we can also support MPI parallel. So if you've got suppose you've already written an MPI parallel. What's MPI? It's message passing interface. It's a certain type of parallelism that, in fact, we don't exploit. We exploit something called shared memory parallelism. So if you've got, for really large parallel machines, you've got MPI codes that somebody's already written. What we can do is we can parallelize the MPI within each node. So for example, some of our collaborators at NASA, they have a 100-core machine. NASA, we are actively collaborating with NASA on some of the stuff as well. So they have a 100-core machine with 8 cores per node. So that's a total of 800 cores. So they've got an MPI parallel program that gets 100-way speed, 100-way parallelism. But they don't have anything going on within each node. We can take this MPI program, parallelize it within each node, thereby getting up to 8x additional improvement on top of an MPI parallel program. So that's it. Brings us to the end of my talk. We have
time for a couple of questions. Nathan.
In the beginning of the talk, you were just mentioning about Intel's built-in parallelism in their compiler. When you were saying that sometimes it produces poor results, do you mean by poor results for a parallel compiler or probe result test compared to the serial? The other
Compared to what the parallel compiler could have done.
Okay. All right.
So the Intel, what I was referring to is the Intel compiler's automatic parallelization plan. What it does is it takes the serial program and attempts to automatically parallelize. That's what I was saying is not as good. It's better than the original serial program.
Okay.
It's not as good as what you could have done with that.
Gotcha.
Now, this is not to say the ICC compiler, the Intel compiler is bad. It's actually a very nice compiler. And it does, for example, spectacularly well on vectorization. You know, the multimedia instruction extensions like SSE, it does very well on it. But it doesn't do very well on it. Yeah.
So when you're using the AESOP compiler to sort of transform these areas of the source code of these scientific programs, how does it also then know that it hasn't essentially changed the answer that that program would give, or that hasn't compromised the program's ability to
Right,
produce
good
the
question,
correct output?
good question. So the way you know that a program is correct is if it, or a transform program is correct, is if it has the exact same data dependencies that the original program had. So let's say you interchange them. How do you know it's still right? Sometimes it's wrong. Sometimes interchanging will lead to wrong results. But there is this well-defined affine theory which looks at the distance vectors before. And based on that, it tells you whether or not interchanging is legal. And if it's not legal, we simply won't do it. So we are only in the business of doing legal transformation. So by design, all those 9 or 10 transformations, in fact there are more, are only done when their legality checks succeed. So that's how it is. You had a question?
Yes, sir. I was wondering, you were talking about how it does benchmarks with different processors and the beginning of the lecture. So with the AESOP compiler, is the assumption that you would have to, if you go to a different machine, say you're using your i7 there, but on my laptop it uses an Intel 2 Duo,
Yeah.
would you have to recompile the code if you move it over to my machine versus using on your machine to get the same sort of results?
Okay, so if you want to get the best possible results, we would have to recompile the code. But there's no, you don't have to rewrite the program. So yes, there's some effort in recompiling, and you know, if my machine has 8 cores and yours has 4, then I mean, you know, 8-way. If I take an 8-way parallel program and I run it on yours, it'll probably work. It just won't work very well because it will put 2 threads on each core, and that context sharing will probably ruin performance. But so you don't have to recompile, but recompiling will give you the best performance. In general, for parallel programs, that's unavoidable. Even if you handwrite parallel programs, you still have to recompile them for every time. So there's no alternative but to recompile under any scenario in parallel computation. Yeah.
So is there any notation for optimality and so is there
Yeah.
if
Is
we
it
imagine
provably optimal? Can we prove anything about it? No. The problem is all of these problems are, I mean, much simpler problems than this have been shown to be NP, meaning that finding the best or proving that you've gotten the best answer is NP complete, which in practice, for those of you who don't know computation theory, in practice it means that the fastest way to prove something is if it's exponentially long, it's called NP. It means that it'll take you essentially forever just to prove that it's, so yeah, it cannot, yeah, there's no proof about this. It's just experimental, quantitative, heuristic-driven search.
so AI cannot help in such things like genetic
Well, I wouldn't
algorithm
say
or-
that, because AI does not, I mean, there are learning techniques, but AI also, for example, if there are learning techniques, it doesn't prove that you've learned in any optimal way. So it doesn't, I mean, we in fact, some of our team was looking at, BA people were looking at that. They were looking at learning based on past experience, what works and doesn't work. But that doesn't give you any proof of optimality either, so yeah, you could use that. Yeah.
What would be the applicability of this for generating code for GPUs or CPUs?
Okay. So honestly, I don't know that much about GPUs, but my understanding is that if you have a shared memory machine, meaning that you have multiple parallel contexts or cores, they all access the same shared memory, you do fairly well. My limited understanding of GPUs is that in addition to that, you've got a network topology that makes stream-like computation more efficient than others. So for example, if you've got a ring network, than if you've got a streaming data that goes from one to the end. You tend to do better. So GPUs, the kind of parallelism we exploit is not streaming. So it may not give you the best performance on a GPU, but if you've got shared memory parallelism like we do, it might apply to GPUs. I mean, that's a question I have to study further. I agree.
Yeah, modern GPUs are single instruction, multiple data, but they can run multiple kernels simultaneously, and they have a memory hierarchy that has local, host memory. There's host memory, which is on the computer side, device memory, which is on the GPU side. There's also shared memory for these groups of cores. So there's
no, but if it's SIMD, do you have multiple independent threads of computation?
Yes. You have single program multiple data, which is
SPM, okay, SPM, not SIM.
Yeah.
Okay.
So it's single program multiple data.
Okay.
So they are independent threads, but they can share.
Well, then, I mean, if they have shared memory computation, I mean, it should apply. I see no reason why it should. But I have to understand a little bit more about the constraints of the networks. I mean, GPUs is a very broad term. I mean, there are many different aspects.
Right, the most modern ones are the most flexible because they come a long way.
Yeah, right.
Uzi,
Yeah,
last
I
question.
think that for the GPUs, you will run into the following problem. Unless you give them parallelism in the hundreds, you end up with a loser. Meaning because they fall behind serial computer.
Yeah, because the cores are lightweight. Is that the reason?
It's because of there's this notion that you have to go around to memory and just for the smallest problem, the smallest operation you do normally on a serial machine.
Right.
It takes you 100 clocks, people takes you 101 clock here.
I see.
Because you have to go to memory.
I
It's
see.
streaming. You have to activate the whole mechanism just to get as if you run 1,000 operations.
Right.
Just for one.
Well, honestly, I won't comment on that. That could very well be true. I mean, in fact, that sounds right. I just would say that the primary target of our work was not GPUs. If somebody can hijack our compiler, I'd be very happy if you can make it work for GPUs. But our primary target was general purpose process.
Well, let's thank our speaker again. Please get a hand out for voice if you have any questions, just come up for